So let's take a look at this this table. And within this table, I can let you know some interesting physics here. So actually, for this part is the metal, or the conductor, and the second part is the semiconductor, and for the third part is typical insulator. Yeah, maybe you will consider, metal is good and the resistivity is low, which means the conductivity is high. So as you can see here, the silver has the lowest resistivity, which means the best conductivity here. So it is a bit better than the copper, while they are all better than the gold. The gold is 2.3 something. And actually, they also have same variation. This is the alpha. This is the portion. Actually, alpha is the portion that this rho will vary according to the temperature change. So they have the same similar temperature coefficient. However, this one I do not know what this is, but actually the alpha is really small. So 4.4 times 10 to minus third is like 0.4%. So this is much smaller, 2,000 times smaller. So, and you see here iron is quite large, 9.68, and this is the platinum, 10.6, almost 8 or 9 times larger, or at least 6 times larger than the silver or copper. So this is the rating of the metals. So here we can see the semiconductor. We have 3 items. The first one is pure silicon, and the second and third is the N-type semiconductor and the P-type, N-type silicon and P-type silicon. You can see here, the pure silicon has a very large resistivity comparing with this one and this one, even though these two is 10 to minus 4, 10 to minus third, which is even 10,000 times larger, 10,000 times larger than the conductor. Actually, we like to use the semiconductor to as the material, as the circuit we use for maybe designing our computer or smartphone or whatever circuit, because the semiconductor is controllable. You know that for the conductor itself, the resistor only depends on the geometric shape, which means that if we really need to have a larger resistor, then we need to make it longer or make the cross-section area to be narrower. However, for the semiconductor, we can try to manipulate the voltage given to its node, and we can vary the resistance of a semiconductor, which is somehow like usually we will use the MOS device, which is like we have a P substrate here, and then we have we have N plus doping here, and then we have another oxide here, and then we have a polysilicon here. So that this forms a traditional called the N-type MOS. And in this case, if we can change the potential at this point, then this voltage or this potential can vary the resistance between this is called the drain and this is called the source. And this can vary the current going through this. In this way, we can make use of this kind of circuit device to do something like logic calculation or even more complicated computation. So this is why, even though the resistivity for the N-type semiconductor silicon is much larger, the resistivity of the silicon is much larger than the conductor. We will use the semiconductor to design our circuits, our chips. And here we have the insulator. Actually, the resistivity is not infinitely large. So as long as the voltage is large enough, there will still be some current going through the insulator. So even though you pick up a light screwdriver, it is not really safe to fix any device if it is switching on. It depends on the voltage difference or the potential difference, and this is the cause. This is the cause, which is 石英 in Chinese. Actually, we use this for a watch, because we can provide some excitation signal so that it will oscillate in a relatively stable frequency, so that we can make use of this characteristic to manufacture our watch. It can provide a relatively stable frequency, so that as long as we divide this frequency, so that we can have an accurate watch. Okay, so maybe I can simply maybe I just skip it at this point. So let's see a sample problem. So a rectangular block of iron has dimension this way: 1.2 times 1.2 times 15 centimeter cube. A potential difference is to be applied to block between parallel sides in such a way those sides are equal potential surface. So what is the resistance of the block if two parallel sides are the square ends, and two rectangular sides with dimension 1.2 times 15. So we will try to calculate the resistance in two cases. For the first case, we calculate the resistance like this. So this is 1.2 of course centimeter, and then this is 15. So this is the first case. So in this case, we have the cross-section area to be 0.012 square, which is 1.44 times 10 to the minus fourth power meter square. So this is the cross-section. So 1.2 times 1.2. So the length should be 15 centimeter. So rho would be R should be rho times L over A. So rho is 9.86. 9.86 times 10 to minus 8th power. And then let me see, times L should be 0.15, 15 centimeter. So over 1.44 times 10 to the minus 4th power. So this value should be 100 microohm. 100 microohm. So this is the first case. And for the second case, we consider the resistance like this. So we have here and this way. So we consider these 2 points. So this is 1.2, this is 15. So here in this case, cross section will be 0.012 times 0.15. Of course, this cross section is much larger. This is much larger. So the cross section is 1.8 times 10 to the minus 3rd power meter squared. And then R would be rho times L over A. So rho is the same 9.86 times 10 to the minus 8th power. And then this times L is only 1.2, which is a 0.012. And then here it is 1.8 times 10 to the minus 3rd power. So R in this case is 0.65 microohm, which is much smaller. 113 times smaller. 116 times smaller. 116 times smaller. So any questions? Yeah, this is the second case. So we have a much larger cross-section area and the length will be much shorter. Okay, so next, Ohm's law. Actually, there are many words here. So actually, the Ohm's law is nothing but V equals IR, and definitely don't need to speak too much. Actually, as long as we have a resistor here, and for some of the device like usually the conductor, it will satisfy this one. Actually, for the semiconductor, it doesn't really match this. It doesn't really match this for the semiconductor. Although for some specific situation, we may approximate using this, using the VIR or something like that to approximate the behavior of the semiconductor, but generally it's not that case. But at least for the conductor, for the metal, as long as we have a metal here as a resistor, so we can measure the potential difference between this point and this point. So this is V, and then the current going through this resistor is I. So V over I is the resistance. So if we have the x-axis to be the potential difference, and the current as the y-axis, so the slope is 1 over R. The slope is 1 over R, or we can simply write it as a V equals IR. And another conducting device, this is not actually a conductor, but actually a conducting device, current can exist in this device only when the polarity is positive. So it is actually not a linear relationship between the potential difference and the current. And when the current does exist, the relationship between ion is not linear. It's not linear. This is very important. It depends on the value of the applied potential difference V. So do you know what this characteristic for? What kind of electrical device has this kind of characteristic, IV characteristics? Do you know? So actually, for this kind of device, it is the IV characteristics of diode. Diode. 二极体。So actually, this is simply connecting a P-type semiconductor with the N-type semiconductor. Then it will have a characteristic like this. P-type semiconductor and N-type semiconductor series together. Then in this way, the current can only go in this direction, which means that as long as the V is higher on the left side, then the current can go to the right side. If the potential difference is lower on the left side, there will be no current going from the right to left. So it makes only current going to the right side, and it is not so strongly depend on the voltage difference. As long as you can see here, actually the current is increased exponentially. Exponentially increase. So suppose the voltage is large enough. Actually, the voltage can't be increased anymore. It's somehow like the current will go infinity large. So for the Ohm's law, it is an assertion that the current through the device is always directly proportional to the potential difference applied to the device. So I is proportional to V, or I equals V over R. So it is very simple. So here is a quick checkpoint. So it asks you, we have two devices. So it asks you, device 1 or device 2 does not follow the Ohm's law. Does not follow the Ohm's law. 1 or 2. 1 or 2. So it's clearly device 2, because this is 4.5 multiplied by 2 is 9. This is 1.5 multiplied by 2 is not 3 here. So clearly 2. Okay, so here we talk about the microscopic view of the Ohm's law. So this is of course a classic derive to the field version of the Ohm's law. Of course, this assumption might not be correct. It only provides an approximation. For some of the equation, but actually it is very classic. So we introduce it here. So here we assume the conduction electron in a metal are free to move, like the molecules in a gas lead to an expression for the resistivity. So if the electron of mass m is placed in an electric field of magnitude e, the electron will experience an acceleration. And actually we assume it is initially stationary, and then it starts to accelerate. And of course, according to the Newton's second law of motion, we have A equals F over m. And according to what we have learned, the electrostatic force is E times capital E, the charge amount multiplied by the electric field, F equals EE. Yeah, so it is an electron, but we just ignore all the direction, ignore all the signs. So we just take a small e here. We only consider the magnitude. So A, this is the acceleration, is EE over small m. And we assume that the drift velocity is this A multiplied by tau. Tau is the average time between collision. Which means initially it is stopped, and then it is accelerated by the E field, and then they may collide with other. And we also assume it to stop again and then try to accelerate again. So in this case, the drift velocity will be A times the time tau, because it is stopped here, and then on average it takes tau to collide the next time. So it will start to accelerate from here to there. So the Vd will be like A times tau. Of course, the average drift speed should be 1/2, but it's just an approximation. So we have a Vd equals A tau. So here, as long as we multiply tau on both sides, so the left side will be Vd. Will be Vd. So we have Vd equals EE over m times tau here. And previously we already know it, J equals NEVD. So in this case, we can substitute this Vd into here. So we have NEEE over m and then tau, like this. So so we try to slightly rearrange the terms, like we move all the term other than capital E over to the left side. So on the left side we have small m times J over N E squared tau. So it will become this way. It may become this way. So of course we hope to get E equals rho J. E equals rho J. Now we already have E and J here. So this term might be an approximation of the rho. And the derivation here is to show that in physics point of view, it should also explain that there should be a constant to relate this one and this one. So m is the mass of the electron, is of course a constant. E is the elementary charge, of course a constant. And then n is the charge density, which should also be a constant for a given material. And tau is the time it takes to collide. So it also depends on the material. So in the other method to show that this is a constant for a given material, and it may vary for different materials. So it is another way to explain the Ohm's law, because when you get this Ohm's law, it is like we try to measure if we have a resistor here, then we try to measure different, we provide different electric potential, and then we try to measure the current going through it. So we can, for this one, we can draw a line, and for another resistor, we can draw a different line, maybe with a different slope, which means different resistance. However, it is just a induction. It's just an induction, which means that we can see this is just like a line. So we assume it should be a line, but actually we should the physician, at least the physician, try to explain this in another way using some hardcore physics. We try to explain that there should be some mechanism to explain that this E and J should be proportional, and this is a constant only related to the material itself. So it becomes the field form of the Ohm's law, and actually it is actually equivalent to V equals IR. Because I can simply show you, because you know that E equals V over L for a resistor, here, as long as this is L, this is A, and this is rho. So we will consider V, which is the voltage difference between this point and this point, and V over L should be E, and then J is I over A. J equals I over A. So for this one we have a rho equals E over J. Rho equals E over J. Rho equals E over J. So that we can substitute V over L here, and then we have I over A here. I over A here. So that we can have V over I over R. Let me see. Sorry. I over A. I over A should be I over A. So in this case, we have V over I here, and then L A. Sorry, should be A over L, because A over L. So we can slightly rearrange the terms so that we have V over I here, and then move A over L to the left side. So we have a rho times L over A, which is the resistance. So which means that we can show it. E equals rho J is equivalent to V equals IR. So this is the circuit point of view of the Ohm's law, which is usually used by circuit designer. And this is the physician point of view. This is the field form of the Ohm's law. So let's see an example. So what is the mean free time tau between the collision for the conduction electron in the copper? So we just simply plug in the equation. Actually we use this equation. Rho equals m e square n, but we move tau to the left side and rho to the right side. So actually we write it like tau equals m over n e square rho. So in this case, for copper, the mass is not copper, the electron, the mass is 9.11 times 10 to minus 31, which is the mass of an electron. And then n is 8.49 times 10 to 28th power, as we calculated before. So E is 1.6 times 10 to minus 19 quantity square, and then the rho is 1.6 times 10 to minus 8, 1.69 times 10 to minus 8. So in this case, it takes 2.5 times 10 to minus 15 second, or you can write it as a 2.5 femtosecond. 2.5 femtosecond. Yeah, so it would be such a short time so that the electron will collide with the nucleus. So you can imagine imagine why the drift velocity of the electron is very slow, as we calculate before. It's like a micrometer per second, because it go for like femtosecond and then collide with the nucleus, and then it will go to the other direction and then collide again. So it makes the electron move equivalently very slow. So for part B, the mean free path lambda of the conduction electron in a conductor is the average distance traveled by an electron between collision. What is lambda for the conduction electron in copper, assuming that the effective speed is pretty fast, much faster than what we calculated before, because that one also concluding that it is something like the average speed. Actually, it moves quite fast, but in different direction, and then it collide. So it is somehow like it moves very fast in different direction, or maybe going back. So if you just zoom in for that short moment, then the speed would be very fast. But in the long term, many velocity will cancel each other, so that overall it looks like it moves very slow. So in this case, we consider the lambda to be V effective times the tau. So it is like 1.6 times 10 to the 6th power times 25 times 10 to minus 15. So which is 40 nanometer. So this is about 150 times the distance between the nearest neighbor atom in a copper lattice, which means as long as we have many copper atom, so an electron here can go through roughly 40 atoms, and then on average, and then it will collide and maybe going back, something like this. And thus, on average, each conduction electron passes many copper atoms before finally hitting one. So here we talk about the power. The power is nothing special. Actually, we can simply calculate by P equals IV, or P equals I square R, or P equals V square over R. We only need to use V equals IR to eliminate one of the variables, so that we have I and V here, we have I and R here, we have V and R here, so that we only need to eliminate one of these three variables, then we can get these three. So actually they are the same. So probably you only need to remember one, and then you can get all three with this V equals IR. And of course, why it will be like this, it is somehow like the potential energy, and then you integrate, you take the derivative with respect to time. So it is like U is the QV. So Q dq is I dt. We assume V doesn't change. So we have IV dt. So if we take the time derivative, so this term becomes 1. So finally is IV. So P equals IV. So we have this expression. So nothing special. So next, semiconductor and superconductor. In this course, we will not talk too much. So actually, semiconductor are material that have a few conduction electrons but can become conductors when they are doped with other atoms that contribute charge carrier. So just now I slightly mentioned the semiconductor. We have pure silicon. Actually, how do we get the pure silicon is we can have something called the SiO2, the silica, and then we try to burn it and then make use of many different chemical material to make it very pure, like it is as pure as 10 to the minus 11. It is somehow like 0.999999 with 11.9 are all silicon. Only the remaining part is the other material. So it's as pure as that. And in this case, as you know, silicon has a 4 valence electron, 4 valence electron, 4个价电子. So in this case, the conductivity is very low, like the carbon. And how to make it N-type? We try to add some 5A element to it, so that it will have one more electron at the valence band. So this electron will become the conducting electron and will be free to move. So that as long as we add some 5A element, 5A value element, 5A 族的元素 5A element to it, then it will have one additional valence electron. Or we can add some, or I should write it as 5A. Or we can add some 3A element to the silicon, so that it will have one less electron at the valence band. In this case, it will look like a hole, because usually we need to have 8 electrons at the valence band. However, it's one less, so that an electron can move to that empty space. So it is just like a free electron, but the other way around, it is called a hole. So in this case, we call it doped or doping. In Chinese called 称杂, which means to add some 3A or 5A element to the pure silicon to make the conductivity significantly increase. So after doping the semiconductor, so with other atoms that contribute charge carrier, in semiconductor N is small but increase very rapidly with temperature. And this is not really important here. And for the superconductor, 超导体 that lose all electrical resistance below some critical temperature. So this figure is the resistance of mercury, 水银 drops to 0 at temperature about 4K, which is minus 269 degrees Celsius. 4K is degrees Celsius. So originally it is linear, proportional to the temperature, or linearly increase with respect to the temperature. However, it suddenly dropped to zero. So it is the superconductor effect. Actually, we really need the fluid helium to make this low temperature. Fluid helium. So below some critical temperature, such material require very low temperature, but some become superconducting at temperature as high as room temperature. So the chemistry or the mechanical engineer try to find some material such that the superconducting phenomenon can appear in a higher and higher temperature, so that we don't really need the liquid helium. Maybe we only need a liquid hydrogen, maybe it already enough. So here we have an additional example. Okay, so we have a cow, we have a man, and then we have a lightning here hitting this point, and then it tells you that the current spread through here in a hemisphere, 半球. And then it asks you that this delta R cow, the distance between the front foot and the rear foot is 1.5 meter, and then the guy here and here it is 0.5 meter. It asks you what is the current going through the person and what is the current going through the cow. So this is a very interesting problem. So first we have E equals rho gram J. So we have rho gram equals I over 2 pi r squared. Because this is the cross section, we assume all the current going to this point and then spread through this hemisphere. So the current density going to this hemisphere is like I over 2 pi r squared. Of course, the current density becomes smaller and smaller when the distance is larger. So all the current are distributed here. However, it's spread through, so the current density is lower at this speed. So in this case, we have hemisphere. So we have a delta V to be minus D plus delta R, and then E dr. So it is the equation we learned in chapter 24. So E using this expression, we have minus rho gram, and then integrate, and then I 2 pi, and then integrate from D to D plus delta R, and then here we have R squared here, R squared dr. So it is nothing but rho gram I over 2 pi, and then we have 1 over R, because 1 over r square, so that it becomes minus 1 over r, so that cancel this minus sign. Evaluate at d plus delta r and d. So finally, the answer will be, let me see, minus log I over 2 pi times delta r over d times d plus delta r. So I person will be delta v, take the absolute value, over r, so which is so this one is log is 100 ohm per meter, and then I is 100k, and then over 2 pi times 0.5 over 60 times 60.5, because we have d equals 60 and this is 0.5, so 60 times 60.5, and then r is 4k, r is 4k, so 4 times 10 to the third power. So the current will be 0.05488. So this current is going through the cow, and actually not the cow, going through the person from here to here. Yeah. So next one, for the I cow, we just only need to change delta R person to delta R cow. So actually, all the calculation remains the same. So we only change the number. So it is yes, like this, and then times 1.5 over 60 times. The only difference is this term 61.5, because for person this is 0.5, this is 1.5, so it is 61.5, and then times 1 over 4 times 10 to the third power, so this is 0.1628. So the current going through the cow is much larger than, actually 3 times larger than the guy. Yeah, and then we have another one. So what is the current of a wire? R equals 3.4 millimeter if the magnitude of the current density is given by this one. So the calculation is not difficult. So for A, IA is integration of JA dot dA. So JA is J0 times R over capital R, and then dA is R dr d theta. So the integration is from 0 to 2 pi for the theta, and for the small r is from 0 to capital R. So this integration is easy. So it is J0 over R times integration from 0 to capital R. We have R square dr, and then we have a d theta from 0 to 2 pi. So in this case, we have a J0 over R, and then this one is R cubed over 3. This is 2 pi. So that it is 2 pi R square over 3 J0. And it should be 2 pi over 3 times 3.4 times 10 to minus third power square times 5.5 times 10 to the fourth power, which is 1.338. So as long as the current is not uniform, we need to use the integration to calculate that. And this is the other case. So IB will be integration of JB dot dA. So it follows everything, and then you turns out to be J0 over R, and then 0 to R, but here we have R minus R times R dR. If you just follow, you just need to substitute JB to be like this, and then we will have a 0 to 2 pi d theta. So we have a J0 over R third power over 2 minus R to the third power over 3 times 2 pi. And then you substitute all the number in, so you can find that it is 0.6678. And which function maximizes the current density near the y surface? And of course, JB, of course, it's JB because if you just plug, JA, it should be JA. Because for JA, it is J0 times R over R. It asks you about the surface, which means R equals capital R. So for this case, it is J0. For JB, it is J0, 1 minus R over R. So when R equals R, this one is 0, this one is 0, this one is J0. So JA maximizes the current density near the y surface. So that's all for today.